All right, so this is 6.1, and we're going to be talking about area between two curves. So we've done some integration now with the U sub and antiderivative, and we understood that the area was between our function to the x-axis, right? That's the way that we typically did it, or our function to the y-axis. But now what's going to happen is if we have two functions, to find the area in between the two of them, that's very easy to do. So this theorem that they have up here, I'll basically show you what's going on with that to break it down. So let's say that we had a graph and we had a function that looked like this, right? I'll call this, since it's on top, I'm going to call it the f of x function. And the area is going to be from there to the x-axis, correct? Now, if I have another function on that same graph, I'm just drawing it on a different graph so you guys can see what's going on, and I did this to it, what's going to happen here is it's going to also find the area under the curve. But now what we're doing is we're going to take these two areas and subtract them from each other so that we get this result that looks like this. And do you see how it's not closed off? The reason it's not closed off because that's my A and that's my B. Now, it could be that they intersect and that closes or bounds the area between them. But if it's not, we need to have equations of x equals A and x equals B to close off the area between the two curves. Does that make sense to you guys? Crickets. Oh, one person put yes. All right. So because one person said yes, I'll move forward. No, just kidding. Let me put it into some concrete examples so you guys can see, and that might be helpful for you guys. So this first example that we have gives us two functions. It gives us the function y equals x squared and the function y is equal to 2x minus x squared. And so if this is my x-axis and this is my y-axis, I'm going to graph it like this so you guys can see where I'm doing increments of halves. So when I'm at 2, I should get to 4. So that's 1, 2, 3, 4. And then this one should be 4 on this side. So this is the parabola. For y is equal to x squared. And then our other function, I'm going to do in a different color. So this function will be in blue. And so that's going to be here at 0, there, and there. And so my parabola is going to go this way with that. Are we okay with that? Do you guys agree with those graphs? Now, one thing I want to show you, and I'll zoom in on this so you guys can see. See how there's a gap between the two functions? That's the area that I'm looking to find. And so we can see that from 0 to 1 is the area that we're trying to find. So that's going to be our lower bound and upper bound. And then all we need to do is find which is the top function minus the bottom function. So that's the way that we do this. So our area is going to be the integral from 0 to 1 of the top function, that's the blue one. So that's going to be 2x minus x squared minus the bottom function, and the bottom function is x squared, right? Oops. That's hideous. And so there's the integral that we're going to use to find the area between these two functions. So when we clean this up, I'm going to get, okay, the integral from 0 to 1 of 2x minus 2x squared dx. I can pull out the 2, so I'm going to get 0 from 0 to 1 of x minus x squared dx. And then when I take the integral of this, I'm going to get 2 times x squared over 2 minus x cubed over 3. And that's going to be evaluated from 0 to 1. We okay with that? Okay.
Yeah.
Okay. So then evaluating this thing, I'm going to go 2 times 1/2 minus 1/3 minus 2 times a whopping 0, right? So that's going to give me 2 times 1/6, which will yield 1/3 units squared. So the area between these two functions is 1/3, whatever the units are, squared. We okay with that?
Yep.
All right. So let's go on to the next problem. And I make the equations a little bit tougher. So now we're talking about trigonometric functions. So you have to be able to draw these trigonometric functions. And I've restricted the domain to be in the in one period interval from 0 to 2 pi. So I'm going to say, all right, that's x, this is y, and I'm going to say that we're going to call that 0. This will be pi over 2. This will be pi. 2 over would be 3 pi over 2. And then this is 2 pi. Okay? Now, I'll make x or y equals cosine of x my black. And so we know for cosine we start at 1. Did that echo?
Yeah, it sounded weird. I can even hear myself.
Oh, someone's got their mic on. So you guys have to mute yourselves. If you don't mute yourself, it will play back to me and echo. It's weird. So you guys have to be careful. If you're going to speak, go ahead and speak, but then after you speak, mute yourself, please. Okay? Okay, so cosine of 0 is going to be 1. Cosine at pi over 2 is 0. Cosine of at pi is a -1. At 3 pi over 2 it's 0, and at 2 pi it will again be 1. Correct? And so my function should look something like this. Now, my next function I'm going to do in blue. And so 2 minus cosine of 0, cosine of 0 is 1, is going to give me 1. And then at pi I'll get a +1, and then at 2 pi I'll get 0. Is that far enough up? I think that might not be. One, two, three. It should be at 3. So it's up here. And then this graph is going to go this way. And we can see that this is bounded at 0 and at 2 pi, right? That's what's going to enclose this thing. It's not a square, it's curved. But we can see that we have this bounded, this region here, right? This is the region that we're trying to find the area for. And so to do that, the integral is going to go from 0 to 2 pi. And our top function is the blue one. So that's going to be 2 minus cosine of x minus cosine of x dx. And so that's going to be from 0 to 2 pi of 2 minus 2 cosine of x dx. And I want the brackets there so that I'm not taking both. And so I'm going to get from 0 to 2 pi, bringing out the 2, 1 dx minus 2 integral from 0 to 2 pi of cosine of x dx. So that will give me 2x evaluated from 0 to 2 pi minus 2 times the integral of cosine is sine of x, and that's going to be evaluated from 0 to 2 pi. So this will be 2 times 2 pi minus 0 minus 2 times 0 minus 0. And so my answer will be 4 pi units squared. Does that make sense?
Yeah, just I feel like it's a little too fast.
Oh, really? Okay, so please ask, what is it that you don't get? Since you guys are staying quiet, I'm just doing it. But what is it you don't understand?
Well, for me, I understand. It's just the writing down the information is like kind of. Now I'm paying attention to, and then I have to write it down.
Oh, got it. Okay, I can take some time, no problem. Correct. Yeah, sine of 2 pi is 0. Sine of 0 is 0, and sine of pi would also be 0. That's why I got both of those to be 0. It's important that you guys know your trig values. Yeah, it's something you guys should have down and know. But feel free to ask me questions on whatever you might not know, and then I can elaborate on that trig for you. But do you guys follow the steps? Do you guys see where it's bounded? That's very important. Is there anyone that doesn't understand that?
The integral of cosine, it's sine of x, or is it negative sine?
So the integral of cosine is sine of x. The integral of sine is negative cosine. Remember, it's the opposite of what the derivative is. So the derivative of cosine is negative sine, but if we have cosine, when we take the integral of that, it's the positive sign. Does that make sense?
Derivative of cosine is negative sine, right?
Derivative of cosine is negative sine, but the integral of cosine is sine.
Okay, makes sense.
Why did you bring the dx to the 1? Oh, I broke it up into 2 of them, and so whenever you do the integral, you have to give the dx for, remember how it's length times width? Dx represents the width, and it also tells us what's the variable that we're integrating for. So the dx goes with it. It's from the definition of the integral that we did. Does that make sense, Carol? You're okay? Okay. Were you able to copy this down, Max?
Yeah, I'm good.
Okay. Yeah, please let me know if I'm going too fast, because I've done this for too long, and so I can forget, and so I want you guys to remind me if you don't understand something, okay? Or if I am going too fast, because this is a whole different world. I mean, I'm sitting here looking at a computer screen, and I know you guys are there, but you know how in a classroom I could look at you and be like, oh, okay, I know someone doesn't get this. Where right now, I'm looking at a computer screen and I see my reflection, and it's like, oh, you get this, so everyone else must be good. And that's not necessarily true. Okay, let me go on to, so for the answer, you would add both answers, right? Yes, so I'll do this. So this guy would be representing the values for the integral from 0 to 2 pi of that 1 dx multiplied by 2. And then this one would be the integral, 2 times the integral from 0 to 2 pi of cosine dx. And that's why I'm subtracting them, because there's a subtraction in between the two functions. So I'm subtracting, but we can call that adding, right, by a negative, whatever. Okay. All right, let's go on to the next thing. Now this is, it's based off of the ruler postulate, so the area between two functions. If we don't know which function's on top, we can always do the absolute value of them. So even if we get a negative answer, we end up with a positive answer between the two functions. But I don't typically do it that way. And I'll show you the way that I do it so that you guys can kind of see. Well, you'll see my method of attacking it. And I like to graph my pictures so that I can see what's going on in the problem, so I have a better understanding. So the example that I'm about to show you will demonstrate that. Okay? So look at this. So if this is the x-axis, this is the y-axis, and I have 4 functions that I'm going to be using. And so let me graph the first function. Is the y is equal to 8 minus x squared. And so this thing's going to look something like this. Then I'll graph the y is equal to x squared. Oops, I got that wrong. Ariana. Oh, I think this is actually at 4, right? Not 3. So it should be up here. So I plotted that wrong, but that's okay. I'll fix it right now. Oh, that's terrible. This should actually be here, not at 3. My apologies. Okay, and then we have x is equal to negative 3, so I'll do that in a different color. I'll do it in green. So that'll be this line right here, right? And it will continue to go on forever. And then I'll do this one in green over here, like that. So we can see, and one of the things I want to stress, we should do what's called a cross-sectional slice. And the cross-sectional slice is just telling me, okay, how's the perspective of this thing being cut up? And this one's being cut in a way that I'm going vertically up and down. Okay, so that red line there is basically just telling me that I have a slice that I'm doing, and I'm doing it on the vertical up and down. And in this problem, I have to do it this way in order to be able to find the area, because if I were to do a slice horizontally, you can see that the slice would hit the function, it would hit the same function on both sides, and we can never have that. So you see how this red line hits the black function and then the blue function? If I were to go horizontally above 4, do you see how if I did a horizontal slice, it would hit the black function twice? Does that make sense what I'm saying? Or do you want me to demonstrate that? Okay, so check this out. So I'll use purple for this. So if I made my slice horizontal and I went this way, do you see that it would hit the same function on the left-hand side and then on the right-hand side? If it hits the same function on the left and the right, if you're taking them away from each other, aren't you always going to end up with 0? So that causes a problem for us, and we cannot have that. So that will help you be able to decide which way to make your slice. Oh, that's a bummer. It deleted my picture. I'm going to make that smaller. Okay. Now, I want to find these regions, and so I'm going to shade it. So bear with me. This is what I'm looking for. This area right here is what I'm looking for. And this region right here is what I'm looking for. So we can see that there's 3 regions, correct? And if I'd have drawn it perfectly, they'd be symmetric. But you can see that there's 3 different areas, right? This is region 1, this is region 2, and this is region 3. Right? So in that furthest left region, my integral is going to go from -3 to this intersection point right here. And that intersection point happens at what x value?
-2.
At -2. Now it's important, I just made an assumption and I want you guys to be able to get this. I just caught my assumption. I just said x value. Why did I say the x value? You can tell me you don't know. It's important.
Can you say the question again? I think I know how to answer it. But...
Sure. So I said what is the x value, and you guys told me -2. I made an assumption that you understood that the integral is going to be in terms of x. Why?
But you said there was 3 regions, so we said -2 because that's where the first region ends.
Okay, but if we had done it horizontally, the cut would have been from wherever this intersection point is in terms of y to this intersection point of y. So it would have been from like whatever this is to this point here. That's
You're trying to stay from -3. You're balanced from -3 to -2. What is it? Y is equal to x squared is the top. and the other one is the bottom, versus on the second section, it's the 8 minus x squared is on top, y squared is on the bottom.
Yeah, but so check this out though. What I'm talking about though is I'm trying to get you guys to understand this. The reason that I went with -3 and -2 has to do with my cross-sectional slice. That red line that I chose, I showed you that it couldn't be the horizontal line, right? Because it would hit itself, right? A function would hit itself. And we can't have that. So because I used the vertical line, what axis does it cross?
The x-axis.
And since it crosses the x-axis, my integral has to be in terms of x. It must be a dx. If the horizontal line would have worked, I could have made it in terms of y. And then these values that I have right here would have been the ones that I'd have to go look for. But since it doesn't work with the horizontal cross-sectional slice, I have to go with the dx. Does that make sense to everybody?
Yeah.
Carol, you said something about I don't get why you picked 3 sections. Here's why there's 3 sections. Do you see that it's bounded at -3 for x and at 3 for x, right? That's where it's terminating. So I have 3 areas that are shaded, right? But notice that the functions vertically are swapping places. Do you see that? Carol, does that make sense? Do you see, like in this region right here, this region number 1, the blue curve is above the black curve, but then in region 2, the black curve is above the blue curve, and then again in the third region, it switches again. Make sense? Okay. So in that first region, then I'm going from -3 to -2. I have to go top function minus bottom function because I don't want to do the absolute value piece to this. So I'm going to go, okay, the top function was x squared, and then I'm going to go minus 8 minus x squared, and that whole thing is going to be dx, correct? Then I'm going to add the next region, so region number 2, and that's going to go from where to where?
-2 to +2?
-2 to +2. Are you guys okay with those values? Okay, cool. Now, what's on top? So it's the 8 minus x squared, and then we need to subtract the x squared that's on the bottom, correct? And then our last one is going to be the integral from where to where? Isn't it from 2 to 3? And then again we swap, so we're x squared minus 8 minus x squared, that whole thing dx. And that's not readable for you, so I'll rewrite that. Okay, does that make sense? And so now I have 3 regions. So instead of doing this absolute value piece here, I'm breaking it up into 3 different sections and doing it that way. People can get caught up with making mistakes with the absolute value integration, and so to avoid any potential mistakes, I just have you guys do it this way. It's a little bit longer, but it's easier for you to see what's happening. Okay, so now we need to take the antiderivative of each of these, and so I'm going to get, let me clean it up. So negative 3 to 2 of a negative 8 minus 2x squared dx plus the integral from negative 2 to 2 of 8 minus 2x squared plus from 2 to 3 of 2x squared minus 8 dx.
On your first factory, is it plus 2x squared rather than
it's a plus. That's right. You're right. It's plus 2x squared. And the thing is you should see that this guy and this guy end up being the same integral, just with different bounds. Do you see that? The negative 8 plus 2x squared and 2x squared minus 8, they are the same thing. It's just they have different bounds. But we know that their area is going to be the same by symmetry. So when I do this, I'm going to get a negative 8 plus 2x to the third over 3. That's going to be evaluated from negative 3 to negative 2. I need to put the negative up there. Plus 8x minus 2x cubed over 3. And that will be evaluated from negative 2 to 2. And really what I should do is this. And then plus 2x cubed over 3 minus 8x. And that's going to be evaluated from 2 to 3. And I leave the algebra to you, but your answer should be 92 over 3 units squared. Does that make sense? Or was I too quick again?
No, makes sense.
Are there any questions? No? Okay. So can I go on to the next one, or are you guys still writing?
Sorry, Professor, what would have happened if we would have chosen a horizontal line instead of a vertical line?
So, like I said earlier, if I had done this line here, do you notice that the function would hit itself there? So when you do the height of the function, right, top function minus bottom function, in that case, wouldn't you get 8 minus x squared minus 8 minus x squared? And what does that end up becoming? That ends up being problematic, right? Because we end up with 0.
Yes. Okay, I see it now.
So that's the issue there. That's where you guys have to be careful, and that's part of the reason why I'm stressing whenever you do these graphs, you should do your cross-sectional slice, and then think of it like a sliding rule, right? You can slide it and see, is it going to hit anywhere and cause a problem? Okay? If we do it horizontally, we run into a problem because it hits itself practically everywhere, right? And so we're never going to get the right answer doing it that way. So let me show you another example. And we'll go from there. And this, I think, will help you guys see the decision factors that are made for doing this. So this is my x-axis, here's my y-axis, and so y is equal to x minus 1 is going to be this guy, right? And so see if I can draw this well. Good enough. And then my parabola, y squared is equal to 2x plus 6. That's going to be something like this. Now, look at this. If we decide to do the cross-sectional slice, right? If I do a vertical slice, do I run into an issue? Like, let's say this was our slice. Would there be a problem there? No problem there. What about if I did it there? No problem there. But what about here? Is there a problem? Right, we end up seeing here that there's a problem, and we can't have that vertical slice. And since we can't have that vertical slice, we're sad. We need to do our slice horizontally. And since it's a horizontal slice, which axis is it going to cross? It's going to cross the y, and so we know that our integral has to be in terms of dy. So now, when we go to decide the bounds for our integral, our lower bound is going to be this number in y, and that is a -2, right? And then up here, that's going to be 4 in terms of y. Now, our functions need to be in terms of y. So our further to the right function was that y is equal to x minus 1. So the only thing we need to do is change it to y's, so it's going to become y plus 1 minus 1/2 y squared minus 3. And then dy. Do you guys get how I got the two functions?
You just solved them to x, right?
Yes, that's right. So I solved them for x, so that my equations that I was going to be using was in terms of y. So then I'm going to clean this up. So I'm going to get -2 to 4, and I'm going to get a -1/2 y squared plus y plus 4 dy. We okay with that? So then when I take the antiderivative, I'm going to get a -1/2 y to the third over 3 plus y squared over 2 plus 4y, and that's going to be evaluated from negative 2 to 4 of this whole thing. But before I evaluate, I'm just going to do it this way. And that's going to give me, let's see, a negative 1/6 times 4 plus 1/2 4 squared plus 4 times 4 minus a negative 1/6 times a negative 2 to the third plus 1/2 a negative 2 squared plus 4 times a negative 2.
On the first, did you intentionally not put the cube for cube? Negative 1/6 times 4. Shouldn't it be a cube on the bottom?
On the first term.
Oh, yes, my apologies. That should be a cube. It was a mistake. Thank you for seeing that. So then that's going to give me a negative 64 over 6 plus 16 over 2 plus 16 minus 8 over 6 plus 4 over 2 minus 8. And then cleaning that up a little bit, I'm going to get negative 32 over 3 plus 24 minus 4 over 3 minus 6. And then I'm going to put everything in terms of denominator of 3. Are we okay with that? I know that one was quite a bit, but I wanted you to be able to see a horizontal slice integration problem because they're coming when we do volumes. So you need to be able to manipulate in terms of dx or dy and seeing which is the easier one to use. You like the dx better than the dy? That's funny. Okay, if you guys are all right with that, I have 3 problems that I want you guys to try and do. So what I'll do is I'll stop the recording here because this is the lesson, and then we can talk much more freely when I start doing these example problems. Is that okay? Or do you guys want me to record the example problems also? I don't care. I just want you guys to be more free to speak. So Carol, you want me to record it? Okay, fine. We'll record them. I just want you guys to be able to talk to me. I don't want you to feel like, oh, because I'm recording, you guys have to be quiet. This is about you guys understanding. And I know when I'm recording, you guys tend to be a little bit more reserved. And that's not what I want. Okay, so let me give you guys the first problem to try. And these are out of your textbook. So these are the two problems, and I want you to find the area between the two. Okay? So y is equal to 12 minus x squared, and y is equal to x squared minus 6. Go ahead and try those, and then I'll do them for you.
No bound?
What's that? I'm sorry?
No bound?
So you're going to graph them and see if they intersect, and if they form a closed region. If they form a closed region, that's going to be your bounding.
Got it. Okay.
So you'll have to graph them to see. All right, I'm going to at least graph them, okay?
Would the graphs intersect at 3 and negative 3?
That's exactly where they intersect. And you guys know you can find the bounds also by just going 12 minus x squared is equal to x squared minus 6, right? So you're going to get 18 is equal to 2x squared, 9 is equal to x squared, and so x is equal to plus or minus 3. That's another way to find the bounds. If you didn't want to graph it, if you were intuitively to know that 12 is bigger than negative 6, then you could see this problem like that. I believe the answer is 72? 72? Do you guys want me to do it now? Okay. So, my integral, you guys have gotten the bounds, is from negative 3 to 3. My slice, we can clearly see, has to be a vertical slice. So we know it's going to be a dx. So the top function is 12 minus x squared minus the bottom function, which is x squared minus 6 dx. So I'm going to get 12 minus x squared plus 6. And that's going to give me 18 minus 2x squared dx. And I'm trying to write all the steps so you guys can see. I'm not going to pull out the 2x. So I'm going to get 18, or the 2. And so from here, plugging it in, I'm going to get 18 times 3 minus 2, 3 to the third over 3 minus 18 times a negative 3 minus 2 times a negative 3 cubed over 3. And so that's going to be 54 minus 18 minus a negative 54 plus 18, which is going to give me 54 minus 18 plus 54 minus 18, which would give me 108 minus 36, or 72 units squared. Are we okay? Is it starting to make more sense now that you're seeing more and more of these problems?
Yeah.
Good, good. Okay, let me give you guys another one. So let's say I gave you x is equal to 2y squared and x is equal to 4 plus y squared. See if you can do this one for me. Easy, but no. Okay. So Carol, do you want to tell me what is it that's got you? I can maybe work with you on the previous problem while people are working out this next problem. The top part of the graph. Okay. What do you mean by that? Like which functions on top, which functions on the bottom? Okay, so the cross-sectional slice is just there so that I can see, it's basically to measure like from this specific point to this specific point, but think of that red line as something that can slide back and forth in the bounded region. Okay? Now when I do that cross-sectional slice, if I were to extend it forever, the axis that it crosses is the variable that I'm going to integrate with respect to. So in this case, because the vertical red line works, I'm going to have an integral in terms of x. Had it been a horizontal line that worked, then it would have crossed the y-axis and my integral would have had to have been in terms of y. So my integral would have been a dy integral. Okay? Now, top to bottom, it's just looking up above minus down below. If you're going with the horizontal, you're going from right to left. Right being more positive, that makes that the quote-unquote top function minus the one on the left being the bottom function. Does that help?
Yes, thank you.
Okay. Okay, so there's our picture. So is it a dy or a dx? It has to be a slice this way, right? Because if I did a vertical, the function x is equal to 2y squared would have hit itself. And so we know that this thing then has to be a dy because of the cross-sectional slice. So which is the further function to the right? The blue one or the black one? The blue one. And so the blue one is this guy. And so my integral is going to go from where to where?
From 0 to 6.
0 to 6? So we're looking at it in terms of y, right? So my y values, that's 1, that's 2, 3. These are negatives. That's 1, that's 2, that's 3. Where is the bounded region's lowest y value and highest y value?
Negative 2 to 2.
So it's from negative 2 to 2. And then it's going to be the 4 plus y squared minus 2y squared dy. And so that's going to give us an integral from negative 2 to 2 of 4 plus y, minus y squared dy, which will give me 4y minus y cubed over 3 evaluated from negative 2 to 2. And that should give me 4 times 2 minus 2 to the third power over 3 minus 4 times a negative 2 minus negative 2 to the third over 3. And what's that going to be? 8 minus 8 thirds minus a negative 8 plus 8 thirds. So that's going to give me 16 minus 16 over 3. That's the same as 5. So it'd be 10 and 2 thirds units squared. Did I do that right? I don't trust myself. 48 over 3 minus 16 over 3 is 32 over 3, which is 10 and 2 thirds. Perfect. Does that make sense?
So where you're finding your bounds of the area is depending on if your graph is cross-sectional with x or y.
So the bounds, so in this case, because my horizontal slice was a horizontal slice, it's in terms of dy, I'm going to be worried about where it's bounded with y values. So in this problem right here, it's the y values where it intersects that I care about. In this example up here, it was the x values that I cared about where it intersected. Does that make sense?
Yeah.
In this example that I did here, I worried about 3 different regions because there was more equations to close off sections. And so I had regions from negative 3 to 2, negative 2 to 2, and then from 2 to 3. And they were all x's because my cross-sectional slice that worked was a vertical slice. Does that make sense?
So what you're saying is it just depends where those functions are intersecting?
Yeah, so that's why pictures are so useful. I mean, I showed you how to do it algebraically here, right? I showed you guys how to do this thing algebraically here. But the thing that ends up happening is even though we know the intersections, we don't know what's on top or the bottom, and so you got to be careful in what you're doing. You know what I mean? And so I like to draw the picture so that I can clearly see. I leave no doubt to what is supposed to happen because I completely understand from the picture that I have. Make sense?
It does. Thanks.
Okay. Yeah. All right. So let's do another one. Oh, does anyone need to copy this work? Okay.
I'm gonna screenshot it.
Oh, no. Please copy it. It's fine. I don't want you guys rushing. It's fine. Just write it down. I want you guys to understand this stuff.
Montiel, not personal. Do you prefer 10 and 2/3 or 32/3 is fine?
Either one of them's fine. I typically go with the mixed number because that makes more sense to me. Does that make sense? Like if I was talking about bags of flour, I could say, oh, there's 10 bags of flour and 2/3 in an 11th bag. Where 32/3, I can't myself, I don't see that as something that's quantifiable for me.
I guess it's like easier to understand.
Yeah, but it's apples and oranges. I mean, well, it's the same thing. They're both fruits. It's just one's easier to see. I don't know. The next two sections that we're going to go through are some of my favorite sections to do, and they're tough though. But they're really, really neat. It's terrible that I'm not a good artist, because if I was a good artist, it'd be fun to be able to like show you what it looked like. So what I might try to do is steal some screenshots from the textbook of some pictures to show you guys, just because I won't be able to do it the justice that you'll need. Yeah. The next section that we're going to be doing is going to be sorry, my wife brought me dessert. It's cool to be at home. It's going to be the washer and disc method that I'm going to be showing you. Oh no, shell to me is definitely something that is easier. But, to each their own. Sharing is caring. It is. They're out there. I think they've got a California Pizza Kitchen butter cake, and so she just gave me a piece. So it's cool, and because I'm recording, every person in the world who watches this video is going to be knowing that I'm having CPK. Oh well. All right. Here's the next problem. So y is equal to x cubed and y is equal to x. So why don't you guys try that one? That should help. No, and the answer is not 0. Part of the reason why I did this problem so that some people would think, oh, odd function is 0. It is not. Nope, not 1 either. Correct. 2 intervals. Because I want to mess with you, is this a horizontal or a vertical slice?
Horizontal?
The answer is yes. It can be either one. You will end up with the same answer. The vertical is going to be the cleaner one to do because it's already in terms of x. But we can do it both ways. Do you guys want me to show both?
Did you show dx first?
Yeah.
And then
Yeah.
do y just to compare?
Yeah, no problem. So then my integral, I'm going to go from, I don't know, I like writing in black. Okay, integral is from -1 to 0. And my top function here is going to be x cubed minus x dx plus the integral from 0 to 1 of x minus x cubed dx. So I'm going to get x to the 4th over 4 minus x squared over 2 evaluated from -1 to 0 plus x squared over 2 minus x to the 4th over 4 evaluated from 0 to 1. And so I should get 0 minus 1/4 minus 1/2 plus 1/2 minus 1/4 minus 0. And so that's going to give me a -1/4 plus 1/2 plus 1/2 minus 1/4, which is going to give me 1 minus 1/2, which gives me 1/2 units squared. Max, what do you mean the 1/4?
Never mind, I thought that was the answer, but
Yeah, it ends up being 1/2. Do you see that? Because I have 1/2 plus 1/2 in the middle, that's 1, and then a -1/4 and a -1/4 will give me the minus 1/2. Right? I don't add left to right. I don't know. I'm bad. But that's the doing it by a vertical slice. If I were to do it by a horizontal slice, we see again it's going to be from -1 to 0 and then from 0 to 1, right? Because that's -1, that's 0, that's 1. If I do it with x's, that's -1, that's 0, that's 1. So my bounds are going to look the same, but my functions are going to be different. Understood? So you guys ready for me to show it?
Yeah.
Okay, so this equation here is going to become the cube root of y is x. That's the only change I need to make to this one. And so my integral is going to go from -1 to 0, right? Because I'm going from here to here. So the one further to the right is y minus the cube root of y dy plus from 0 to 1, because now I'm going from here to here. And now the cube root of y minus y, because the cube root of y is further to the right. Is that understood?
Why did you change the value to cube?
Oh, because it was y is equal to x cubed, and since I'm going to do dy's, I need to make my integration cubic, because I need it to be in terms of y, because I'm in the dy integration. Everything's in, the variable has to be in terms of y. Does that make sense, Alan?
Yeah, I see that now.
Okay. So then when I take the antiderivative of this, or the integral, however you guys want to say it, that's going to be the 1/3. So it's going to become y to the 4/3. So this will be 3/4, evaluated from -1 to 0, plus y to the 4/3 of 3/4 minus y squared over 2 from 0 to 1. And now we have to evaluate this. So it's going to be 0 minus -1 squared over 2 minus a -3/4 to the -1 to the 4/3 plus, and this one should be in brackets just so that I'm good notation for you guys, 3/4 to the 1/4 minus 1/2 with that squared, and then minus 0, correct? So that's going to give me a negative 1/2 plus 3/4 plus 3/4 minus 1/2. Let's see, did I do that right? Oh no, this should be, I believe that should be a minus. So I'm going to get a minus 1/2 plus 3/4 plus 3/4 minus 1/2 is going to give me, I'll just write it this way, 6/4 minus 4/4 is going to give me 2/4, which is 1/2 units squared. Are we okay? So you can see that doing it either way, we will get the same answer. provided you can do it both ways. Are we good?
Montel, I have a question in regards to working on this with the calculator.
Uh-huh.
Do you mind, or do you want us to, or I don't know how to explain, or do you want us to do a graph drawing? But can we use the calculator to do it? To find at least the bounds where they intersect?
Oh, no, that's fine. Here's the thing that's going to happen, though. At some point, we will end up back on campus, and your professors will want to see work. So you've got to get yourselves in the habit of doing this work. The algebra skills that are developed in this silly arithmetic here ends up being worthwhile. I know it doesn't seem like it, but it will long term.
Okay, but let's say to check the work.
Oh no, you should always check your work, for sure. Now, one thing you... well, with your TI-84, you can type it all in as one function and it will work. So you should be able to get that right. If you did it with your calculator, you should have gotten that answer of 1/2, right?
Yeah. Now I guess like my second question was, I mean, I don't know how to do the dy. You know how it's like the graph is rather in x is equal to y, whatever.
So how I changed it from this to this? Or you're talking about the picture?
Oh, I guess I can do that. But I mean, I thought you could have like done it, because you know how in the graph, in the graph section, it's y is equal to in terms of x. But is there a way you can do it in terms of y?
I guess I don't understand what you're saying, because I just did it here in this top one to the right of the picture. That's in terms of x, and I got 1/2 units squared. And then down here, I did it in terms of y, and also got 1/2.
No, I understand what you're saying, but I mean, like, me being lazy,
Mm-hmm.
as in like putting it in the y equals in the calculator.
Uh-huh.
Is there a way to put it of like x equals rather than?
Oh,
y?
understood. No. No, so what you could do, because your calculator doesn't know what the variable is, you could just change your y's and call them x's, because it's a variable, right? If I gave you z's and we're in the z domain, xz, you just, in your calculator, put it in as x. Who cares?
And then flip the calculator sideways.
Well, you don't even need to do that. The way the graph is going to be, so like check this out. This graph here, right?
Correct.
If I changed, and you can do it right now, make it y is equal to 2x squared and y is equal to 4 plus x squared. If you were to do it that way and then find the area, take a guess what the area is going to be.
Oh, that's right. But just do it in dx, right?
That's right. It's just for understanding, and this is why it's important, because there's going to be times where you're not going to be able to change. So I want you to understand what the cross-sectional slice is doing to be able to find the area. Because eventually when we get to 6.2 and 6.3, I'm going to be pivoting around an axis, and you're going to need to be able to find that area to know how to pivot that and rotate it around whatever I call the axis of rotation. So it is an important habit for you to do, but if you want to check it in your calculator, the way you check it in your calculator is turn everything into x's. Understood?
Yeah, that makes sense.
Okay, I'm going to stop recording so it's not crazy long, and then I'll stay on and answer questions for you, but I'm going to stop the recording, okay?